All right, so in this lecture, we're going to cover live migration of virtual machine. So this is part 2 of the lecture. In the first part, we had talked about the basics of live migration. I will quickly cover that. We won't go over all the details. And then we will go into the main key techniques, post-copy and pre-copy, and various variants of these two techniques. Okay, so last time we looked at what exactly is live migration. Here we have a virtual machine that's running on one physical server, and then we want to move it to another physical machine. But then we want to do it as the VM is running. We don't want to shut down the VM and have the user experience any downtime. So our goal in live migration is to keep the VM as live as possible, executing for as much time as possible. So, and then we talked about how, when migrating a VM, you have to move the CPU state, the IO state, and the memory state. And of all these three, the memory state is the biggest component of live migration, because VMs may have gigabytes of memory, and copying over all the memory state will usually take time. So most of these techniques differ in terms of how they migrate the memory state, because CPU and IO state are very little. They don't take as much time to migrate. So as the picture shows here, that we have a migration manager at the source machine that runs besides the VM. So for every virtual machine, there is some sort of a migration manager process. And then at the destination, there's another migration manager process. These two processes talk to each other through a TCP connection. And so the source migration manager would take the VM's memory contents and CPU IO state and transfer it over the TCP connection to the destination. At the destination, the VM would reconstruct the migration manager would reconstruct the VM's execution state from all the data that it receives. Okay, so we talked about why people might want to do live migration for various reasons. You might want to shut down a physical machine, so you want to move the VMs over. You might want to do load balancing and so forth. So whatever the reason, usually the requirement is that VM should not experience much disruption. So we talked about various metrics for live migration, and among these was, the primary one was that, we want to minimize the downtime. Downtime meaning the amount of time for which the VM is not running. But then in some cases, we may also want to minimize the total migration time, meaning from the start of the migration command to the end of the migration. How long does it take till the VM is running at the destination side? We also want to avoid interference with other VMs running at the source or the destination machine, because VM migration is a resource-intensive activity. So it can adversely affect other VMs in the system. So you want to minimize that as much as possible. And then, of course, we also want to be considerate to other machines running in the system, other machines running on the network, because we are going to use a lot of bandwidth over the network to transfer the VM state. Okay. So last time we looked at two techniques, pure stop and copy and pure demand paging. So here, these are two extremes. None of them is completely live, but they serve as a useful starting point. So in pure stop and copy, you first stop the VM at the source, then transfer all its state to the destination. And then once everything is ready at the destination, then you start the VM at the destination. So obviously it's not live, because during the entire transfer phase, the VM is stopped, not running. right? So the advantage of this technique is that it has minimal total migration time, right? And but then the disadvantage is that it has a very long downtime, right? So in this case, it so happens that the total migration time is equal to the downtime. So if your goal is to move the VM over in the least possible amount of time, and you don't care about the disruption, then the best approach is to do pure stop and copy. But if downtime is important, then this is not a good choice. The other approach is pure demand paging, where in theory, you can have the VM constantly running at the source machine, constantly running during the migration. But there are certain drawbacks to this approach. So what we do is we take the VM from the source, we first stop it, but then move only the CPU and IO state. And most of the memory state we leave behind at the source machine. So, and as soon as we have copied over this minimal execution state, then we would, once at the destination site, we would immediately set up the VM, pretend that it's already there, and then start running it. We have all the program counters, registers, in the bare minimum execution state. But as soon as the VM starts running, it would try to access its memory, which is not yet there. So as a result, it would start causing page faults. So in this case, we'll have to pull the memory contents from the source side, right? So the destination migration manager would then request the source migration manager that there's a page fault, I need this particular page of memory, and the source would then send it. So as and when page faults happen at the destination, those page faults are serviced over the network from the source. And this technique, although you get the VM running at the destination almost right away, but it would take a long time to service each page fault. So the amount of time, so what we have taken is we have taken a long downtime from the first approach. From this approach, we took this long downtime and then we broke it into small pieces and we converted it into time taken to service page faults in the second approach, right? So the VM would be running in theory, but it will be really, really slow, okay? So, this approach, so this technique, so we have these two different extremes, and now we are going to see, how we can do better than these two techniques. All right. Any questions so far? All right. Okay, so first we're going to look at this technique called pre-copy migration. And in pre-copy migration, the goal is to have minimal disruption to reduce the downtime. And the way we will do this is that we will keep the VM running at the source machine, and we would start sending the memory over to the destination first. So in the background, as the VM is running, we are copying the memory over to the destination. And then once we are sure that all the memory is at the destination, then we are going to transfer the CPU and IO state. So in the very beginning, we don't freeze the VM, so we don't freeze the VM, we let the VM continue to run. It's accessing memory, performing read and write operations to its memory at the source machine. And in the background, the migration manager goes over every single page in the VM's memory and starts sending it to the destination, right? So, so what will happen as you start sending the first, in the very beginning, you start from page 0, and then send it over page 1, page 2, and all the way to the last page. So that's the pre-copy round shown here in this figure. The very first round, it will take a long time because there may be many pages to send. But then once all these pages have been sent, to the destination, we may find that, hey, in the background, the VM was running. So it had actually gone back and dirtied some of the pages that we had already sent. For example, if we sent page 0, and then we are going ahead and sending page 1, 2, or 3, the VM may go back and dirty page 0. It may write something to that page 0. So the copy that we sent to the destination is not up to date. It has been changed since it was last sent. So what are we going to do? We have to track the pages that were dirty. So during this round 1, some pages may have been dirtied. So we have to somehow figure out how these pages, dirtied pages, which of these pages have been dirtied, and then we'll have to send them again in round 2. So in round 2, we're going to go over the memory pages again, but we'll this time only send the pages that were dirtied during round 1. So if there are pages that were dirtied here, they will be sent during round 2. Likewise, when we are sending pages in round 2, some pages may be dirtied again. So we are going to send those pages over in round 3, and so on. And as you can see, we may need multiple rounds of pre-copy before we figure out that we have sent all the pages and there are no dirty pages. Okay, so this is kind of tricky because it may so happen that as we keep sending pages over multiple rounds, in every round the VM may be writing to its memory or some other pages. So actually these rounds may never finish. They may never converge to a small enough number of pages where we can stop the VM and send it. All right. So at some point, say there's a maximum number of rounds set n, let's say. Once you reach n rounds, you can say, all right, I've tried enough and I'm going to stop the VM, stop the VM's execution at the source. And then I'm going to send CPU and IO state, and that phase is called downtime. So in the downtime, you're going to send the CPU state, the IO state, the state of the IO devices, any registers, program counter as part of the CPU state. But then you might have some leftover dirty pages from the last round, from the nth round. There may still be some leftover dirty pages, and hopefully they're a really small number of pages, right? So those remaining dirty pages would also be sent during the downtime. If we can keep this downtime really small, primarily because the remaining dirty pages in the downtime are really small, then the VM would be paused for a very short time. And as soon as the rest of the state is received at the destination, the migration manager can then resume the VM. When it resumes the VM, all the memory is there, everything that's needed to run the VM is already there, and the VM can start running at almost full speed right away, right? So that cold start penalty of running the VM at the destination, resuming the VM at the destination would be very small. So this is called pre-copy migration. The pre part here means that the memory of the VM is sent before the CPU and the IO state are sent during the downtime, right? So by sending majority of the memory before the CPU and IO state is sent, we make sure that the destination is ready to start running the VM at nearly full speed. Okay. Any questions so far? How this approach works? So there's a question from Aditya: what happens if the VM crashed while migrating over the network? How to recover from this? Is it possible to just leave the failed VM and start from the migrated VM? I mean, VM can crash anytime, right? And and not just during migration. So the question really is, if your VM crashes, is there a way to recover your crashed VM? And there are various high availability solutions or fault tolerance techniques that are implemented that look very similar to live migration. Essentially, you have to take a picture or a snapshot of your VM at some regular instance where the entire state of the VM is consistent. and then save those snapshots. So if your VM fails, you can resume resume the VM from the snapshot. Of course, you have to be careful that the snapshot is consistent. Snapshot shouldn't take you back in time where you have to undo certain external operations. So for example, you may have written to a file and then certain content, but then after a failure, if you roll back to before the write operation, then you have lost some data that was written to the file. So this has to be done carefully. So it's a generic problem, not specific to VM migration. And pre-copy approach is kind of better. In this case, if the VM running at the source dies, you can just use regular snapshotting mechanisms to recover. Destination doesn't have anything during the migration that you really need to worry about, right? Only after the resume operation is done, VM is resumed, then the snapshotting has to be done at the destination. So it's not, for pre-copy, it's not a big concern. For post-copy, we'll see that there's an additional concern of failure during migration, right? But since we haven't discussed post-copy yet, I'm going to hold on that part. Does that make sense? Okay. Any other questions about pre-copy? All right. So as you might notice that the duration of downtime, it depends upon how much dirty memory is sent during the downtime. It means in the last round, if there were very few pages that were dirtied, then the downtime would be very short because there are very few pages to send during the downtime. But if there are a large number of pages dirtied in the final round, then this downtime will take a long time, right? So you can think of an adversarial scenario. There's a VM that's constantly starting from its first page and then dirtying all the pages. So by the time you finish round one, in round two, again, all the pages are dirty. So you have to send all the pages over again and again and again. So that's a very unusual scenario, but sometimes certain write-intensive applications or data-intensive applications might end up with that kind of scenario. So although pre-copy is nice for most applications, but it works only as long as majority of the memory memory operations are reads. So there are more reads than writes. So if there are lots of write operations during these pre-copy runs, then this pre-copy migration is not going to help. The final downtime would be almost as good as stop and copy, because if you have to send all your pages are dirty, you have to send all the pages over during downtime again, then all the work that you did ahead of time during pre-copy rounds was useless, right? So it doesn't always work, right? So we have to think about scenarios where there are write-intensive applications, and how do we migrate VMs that are running write-intensive applications. Okay, there's another question from Harshit. How does memory migration process at the source keep track of those pages that were dirtied only during the previous iteration? Yeah, it's a great question. Thanks for reminding me to answer this. And this also relates to the question that was given to you in the assignment. How can the OS track dirtied memory pages, right? So what does the OS, and of course the migration manager in coordination with the OS, how do they track the pages? So during round one, like VM is accessing its memory, it's reading and writing, but specifically for write operations to the VM's memory pages, we want the OS and the migration manager to, the hypervisor and the migration manager to track which pages have been dirty. So the way to do this would be just as what we did in the super page paper. If you remember, in super page paper, we had a similar problem that whenever a process writes to a super page, we want to trap that write so that we could demote the super page, right? So the same technique we can use here. So whenever a VM, so before we start the pre-copy round, we would mark all the pages. We would mark all the pages as read only. All right. So so now what happens if the VM starts doing write operations on certain pages at various times? Then each of these write operations, the very first write on any page, would cause an exception, right? And whenever there's an exception, the OS gets control, and the OS can then note down that this particular page is not dirty. But it doesn't just note it down. The OS would also convert the page to read write. So since it has noted down that this page is dirty, now it can convert the page into read write, so that future write operations don't on the same page don't cause an exception. And likewise, for every page, the first write would cause an exception, and the subsequent writes would not cause an exception. So you can maintain a list, kind of a bitmap of ones and zeros for various pages, and this bitmap, what's also known as, I would say, a dirty bitmap. Excuse my handwriting, I'm writing this on the iPad. So yeah, the dirty bitmap would then be carried over to the second round. So in the second round, what we will do, you will mark all the pages as read-only again, but then you would also get the bitmap from the previous round, and whatever pages are marked in the dirty bitmap, those would be sent during the second round. In the meantime, the second round is getting its own bitmap. I'm just going to write BM for bitmap, and whatever is collected, the bitmap collected in the second round will be sent to the third round, and so forth, right? So, and of course, the bitmap collected in the last round would be sent during the downtime. So the key is that at the beginning of every pre-copy round, we're going to mark all the pages of the VM as read-only, and then track write operations on the entire VM's memory. Okay, does that make sense? So of course, this also means that every write operation is going to cause an exception, right? Every first write operation on any page in each round is going to cause exception. So in a way, write operations are becoming more expensive. So although the VM is running, but then write operations are slower than what they're supposed to be. And since we are resetting the bitmap to read only upon every iteration, then that's also going to add up at the boundary of each iteration. So pre-copy is not free. So as long as your VM is mostly read intensive, this will work fine. But as soon as there are more and more write operations, you will start seeing a slowdown. Okay. Any other questions on this? Okay, so yeah, so the next slide is what we just discussed. How do you track the dirty pages? So you would mark all the pages as read-only at each iteration. Then you would track the first write operation to every page. So the hypervisor would then, so in Zen, there is this process called ZenD, the migration manager, which tracks. In KVM, there's this migration manager called QEMU, which tracks these dirty pages. And as I mentioned earlier, this works well only as long as the writes are infrequent. So if the application VM happens to be write intensive, this whole pre-copy mechanism would be, of course, slow, but also ineffective because the downtime would be unusually large. Okay. So you can do certain things to pre-copy to make it better, work better for write-intensive operations, right? So first of all, we are sending the memory of the VM many times, right? We are repeatedly sending round one, round two, round three. And it can take up a lot of network bandwidth. So one of the common optimizations that people do, and this has nothing to do with write-intensive or read-intensive, but one common optimization is to limit the amount of bandwidth that the migration manager can use. So if you have, let's say, a 1 gigabit per second network, and then migration manager will be limited to say only 200 Mbps, right? So that way you don't, the other applications can still use the rest of the network bandwidth. You want to limit the impact on other VMs running on the same machines. So you can choose to limit the bandwidth used by the migration manager. Of course, if you do this, then what that means, if you limit the bandwidth used by the migration manager, that also means that you're slowing down the rate of memory transfer, which means you're increasing the total migration time. Okay, so this doesn't come for free, but you can certainly reduce the impact on other VMs by limiting the network bandwidth used by migration manager. Specifically for write-intensive applications that we talked about earlier, one of the optimizations that particularly Zen uses is to stun rogue processes. What does this mean? Rogue processes are processes inside the VM that are writing to the memory. So if you know that a certain process is writing a lot to memory and it's getting in the way of pre-copy migration completing its job, then you can ask the guest OS to pause or stop those processes for the duration of the migration. So that if you stop those processes, then you don't have any more dirty pages, which means that your pre-copy rounds can finish quickly. And then once you move the VM to the destination, then you can restart those rogue processes. So rogue, not in the sense that they're malicious, but just that they're dirtying a lot of memory and that's slowing down the VM migration. Another technique to reduce the amount of traffic you send over the network, a lot of the pages inside a VM are kind of garbage. They don't have anything useful. So you take if you look at all the pages that are being managed by an operating system, a lot of them are free pages, like a pool of free memory pages that are used to give to processes. So for a VM, when we're transferring a VM, we don't want to transfer all these useless pages that are just free pages, because they can always be reallocated at the destination. So another common optimization is that before migration, you can ask the VM to dump all its free pages. And so that way you can shrink the VM's memory footprint to just the pages that are being used. And then you only transfer these over to the destination where it starts running. So this can greatly reduce the memory footprint of the VM. If the memory usage is fairly low within the VM, then freeing the page cache pages can help with the destination, with the migration. Okay, so of course, this also means that especially the last two techniques, stunning rogue process and freeing page cache pages, they also make this migration mechanism non-transparent. What that means is the guest OS now knows that it's being migrated from one machine to another machine. Right? One of the goals of live migration is also to ideally keep it transparent, meaning that we don't want the user or the applications in the VM to realize they're being migrated. But if you want to speed up live migration, you may have to implement certain optimizations like these two that might make the process migration non-transparent to the VM. Okay. Any questions so far? Okay. So this brings us to the second technique called post-copy migration. And here, so why do we need one more technique? Well, with pre-copy, we saw that, we have multiple rounds of memory transfer. The same page may be transferred many times with pre-copy over the network, so it increases network traffic. And of course, pre-copy is not friendly to to write intensive applications. So we want to solve these problems with post copy. And the way we are going to solve this problem with post copy is to say that, well, why we want to send every page only once to the destination. We don't want to send it again and again. So one of the ways we can achieve this is by having the VM execute at the destination right away. So just like the pure demand paging approach that we saw in the beginning, the extreme case. So here we are going to uh, stop the VM right away. So in the preparation phase, the very first thing we do at the source machine is to stop the VM. And then we will take the CPU state and IO state and minimal number of non-pageable memory. Non-pageable means that these are memory pages on which you can't have a page fault. You can't have the VM execute a page fault, right? For example, DMA pages or certain print pages of the operating system. So we'll take some minimal execution state and move that over to the destination. And this is guaranteed to be very small, this downtime, because we're moving very little state over to the destination machine. And as soon as the VM reaches the destination machine, we're going to start the VM. At this point, we're going to resume the VM at the destination. So of course, as with the pure demand paging approach we saw, when the VM starts running, its memory is still back at the source, so it's going to start doing page faults. And like in the demand paging approach, we have to, the source migration manager has to ask, sorry, destination migration manager has to ask the source manager, can you please give me this page? I have a page fault. And of course, the source can send that over, right? But if you just rely on page faults, then it's going to take a really long time to get all the pages over. Right? So post copy does one more thing. So of course, it does demand paging over the network, but to speed things up, it's also going to, the source manager will actively push the pages from the source. So instead of waiting for page fault requests from destination, it's going to say, I'm going to send all these pages anyway to you. And then in the meantime, if you have a fault on some other page, you can ask me, right? So as demand paging is happening normally, at the same time, the source manager is pushing all the remaining pages over to destination. So with these two techniques, demand paging and active push, we can guarantee that every page goes over the network only once, right? Not multiple times as in pre-copy. And one of the goals of this active push phase is that you want to send a page over to the destination before the VM faults on it. So if you can guess ahead of time what pages are going to be needed by the VM right away, then you can hopefully send it to the destination before there's a page fault on it. And if to the extent that we can send the pages before a page fault, there will be fewer page faults over the network, right? And that way, hopefully, if our active pushing algorithm is good enough, then hopefully there'll be no network-bound page faults, and then the resumption time at the destination would be really fast. So these are some of the advantages. You have each page is transferred only once, and the total migration time is deterministic. In the case of pre-copy, we don't know how many rounds of pre-copy we have to perform before we can do downtime. Here, we know that the downtime is constant, very minimal state. And then in the post-copy phase, every single page is sent only once. So no page is sent more than once. So again, the amount of time needed to do the memory transfer is also constant. So you can pretty much guess ahead of time what's going to be the total migration time. Okay. Of course, the disadvantage is that there's a cold start penalty at the destination, and then this also cold start penalty, meaning that at the very beginning there may be a few network page faults till active push catches up. So very few in the very beginning. You may have VM's memory accesses will all go to the destination source and service over the network, but as active push sends more pages over, you will have fewer and fewer network page faults. And then the last point is about what if the migration fails. And so this is problematic for post copy. because now for some part of the migration, you have the VM state being split across the source and the destination machine, right? So when we move the CPU state over to the destination and started executing the VM, so the most up-to-date execution state, the program counter registers and all that stuff were at the destination, but all the memory was at the source, right? So now the VM is split over two machines, and that's a problem because if one of these two machines dies, then we have lost part of the state of the VM that can't be reconstructed back. So, uh, so this is not as resistant to failures, right? It's more vulnerable to failures. Or let's say even the machines don't die, but the network dies, right? So then suddenly, the source and destination can't talk to each other, so the VM can't get its pages at the destination from the source. So your VM is, you've lost your VM, and that's a pretty big deal. Like if you're running on the cloud platforms, your customer gives you a VM, use post copy to migrate it, and sorry, my migration, lost your VM. So, so you need some extra mechanisms to make sure that we don't lose VM. So we're not going to go into those fault tolerance techniques. They make post copy more complex. Again, it depends. Instead of taking a snapshot like we do for normal fault tolerance, here we have to do incremental snapshots of the state from both the source and destination. Okay, but hopefully, since we have reduced the total migration time from the start to the end, so hopefully the amount of time for which you have to worry about failure is very, very small, right? Um, all right, any questions on this so far? Okay, so so there's just an interesting anecdote. So Google published a paper recently, a few years ago rather, where they described how they do live migration in their cloud platform in Google Cloud, and they, as expected, they mostly use pre-copy live migration, but then they mentioned that for write intensive applications they actually do post-copy live migration. And very interesting, at least in their paper, they say that they actually end up losing some VMs. They do millions of live migrations all the time, but then sometimes they actually end up losing VMs. Sometimes the migration just fails. In that case, they just throw up their hand and tell the customer, sorry, we screwed up, which is very interesting to me. All right. So I'm going to go to the next slide. Of course, you can take a hybrid of pre and post copy, and this will have the benefits of both and also the disadvantages of both, right? So, so what a hybrid migration would do is that you would, just like pre-copy, you would do a few pre-copy rounds, but then instead of having indeterministic, non-deterministic number of pre-copy rounds, you can limit the number of pre-copy rounds that are performed. So maybe 2 or 3 pre-copy rounds, that's enough to send majority of the pages over to the destination. And then you can pause the VM, send the minimal execution state, and then there's still some pages left over, some dirty pages left over at the source. During this downtime, we are not sending any remaining dirty pages. We leave them behind at the source. And at the destination, when the VM starts running, we are going to start executing the VM, but in the background, we are going to fetch the remaining dirty pages over the source. So since the remaining dirty pages over the source are very few, hopefully the active push phase would be fast. And hopefully there will be very few network-bound page faults, right? So that's the advantage. You're keeping the downtime low. You're not transferring dirty pages. During the downtime, you're only sending some non-pageable pages. But then you're also having a very fast active push phase. So the whole mechanism from the start to the end, total migration time, can be deterministic. Okay, it will be longer than for pure post copy, but it will be shorter than for pure pre copy. Okay, and this can handle write intensive applications. But of course, you still have the problem that for a short duration of time, the VM state is split, just like for post copy. Like you leave behind some dirty pages here, and then you fetch them at a later time once the VM starts running at the destination. So, um, so there's a small window of vulnerability, just like post copy, but hopefully that window is small enough. So most major uh, live migration, most major hypervisors provide all these three approaches: pre-copy, post-copy, and hybrid pre-post-copy techniques. Okay. Any questions on this? Anything that's not making sense? Everyone is unusually quiet, which gets me worried. Okay. So there's another aspect of liveness, which is that you want the remote users of a VM to be able to interact with the VM uh, and not observe any downtime due to the migration. And this can be challenging because you have TCP connections that are established to the VM. Let's say that these are you have web access requests. You're running a web server inside a VM, and there are clients interacting with the VM, and just suddenly you're migrating it. What if their TCP connection breaks? Then suddenly people are not able to access their websites, excuse me, or databases and so forth. So, so all the live migration mechanisms go to great lengths to maintain network connection. And there are certain network specific issues that you need to consider when doing live migration. So there are two cases that we need to worry about. One is in a local area network. That is, you're migrating a VM within the same network from, say, one part of the network to another part of the network. And then there is wide area network where you're migrating the VM across geographical distances from one subnet, one IP subnet, IP network to another IP network. So for example, from East Coast to West Coast, or from Europe to US, and so forth. So in both cases, there are different approaches to maintain liveness of network connection. The easier case is within the LAN. You can, you can pretty much take any machine in a Ethernet, plug it out from the Ethernet socket, and plug it into another machine, and your network will be alive. And if you do it fast enough, your TCP connections may also not time out, right? But in the case of VMs, we just don't want like multiple seconds of downtime. We are targeting like just tens of milliseconds of downtime that the TCP connections won't notice. So so there are some additional technique called unsolicited ARP that are used. What that means is that when your VM moves to the destination, instead of waiting for the network to discover that it has moved, it would send out a broadcast message. An ARP message is something called an address resolution protocol message. And that's usually used to map Ethernet addresses to IP addresses. And that's used all the time. If you do a packet sniffing on your network, you would see ARP messages are flying around all the time. But what the migrated VM does is when it reaches the destination, the hypervisor would send an unsolicited ARP message to the rest of the network saying this VM has moved to me, right? So that way all the switches and all the other hosts in the network know that a VM has moved to another physical machine. So, and this, by doing this unsolicited ARP, you can cut down the network discovery time significantly, right? you may still lose some packets that were being sent to the source machine. When they reach the source machine, the VM is gone. So they're just dropped. But then hopefully TCP can recover. TCP is a reliable connection-oriented protocol. So if there are just a few lost packets, TCP can recover from it and then try retransmission, and then those packets will be resent. So this is not a big problem. But there's something to keep in mind that you might come across in other contexts. Also, sending an unsolicited ARP to speed up network discovery. Okay, but also that's also a security hole in IP protocols, but we're not going to get into that right now. In the wide area network context, you're of course moving your VM across large geographical distances. So of course, there's the issue of storage migration, which is a separate issue, but also you had some TCP connections to say East Coast, and now you're moving them over to West Coast. You also want to migrate all the live connections. And that can be challenging. It's not just enough to have unsolicited ARP, because now you're not sharing the physical subnet anymore. So ARPs won't work. You have to set up tunnels, just like you have virtual private networks these days. So similarly, you can tunnel the VM's traffic from the source to the destination. And if you have a cloud provider who has very fast, low latency, long distance network links, then they may be able to provide this capability to you. And of course, any new connections that you establish, you can establish directly with the destination. Okay. So this is just to give you some sense of what are the underlying issues involved. And if you're curious, you can dig deeper into these. Any questions on these? Okay. So I mentioned storage a little while ago. If a VM has a virtual disk where all its file system and data is stored, so if you're migrating the VM within the local area network, usually storage is accessed over the network from a remote storage device, such as a network file system or a network block device or iSCSI. So if a VM was able to access storage at the source machine, it will also be able to access it at the destination machine. So it's not going to be a problem for the VM to access the storage. But over a wide area network, of course, storage may not be shared over the network. So you may have to also copy the disk image over. And there are various optimizations. Just like for memory, we use pre-copy or post-copy. Similarly, for storage, we can again use pre-copy or post-copy, but for disk images, the contents of the disk. And since large amount of data is being transferred over long distances, again, you can compress data, you can do deduplication, which is another technique for saving network bandwidth, and so forth. Okay. So again, LAN migration versus WAN migration are two different. There may be different design of the underlying migration techniques. Okay. Any questions? Okay. So if you read the original paper on live migration for Zen, you would notice that there's a technique described called self-migration. And the idea right now, the techniques we are discussing, they depend upon the hypervisor. The hypervisor needs to migrate the VM to the destination. But sometimes, you don't want to depend on the hypervisor. Sometimes the VM can migrate itself, right? So you want to have hypervisor independent approach to migrating a VM. So for example, let's say you want your VM is on Google Cloud, and then you want to migrate the VM over to Microsoft's Azure Cloud. These two different cloud providers from different companies won't talk to each other because they're competitors. They won't let you migrate. But then the VM can implement mechanisms to migrate itself from one cloud to another cloud. That's self-migration. And here the idea is that you just implement the migration technique inside the VM itself, inside the guest operating system. And the techniques that we discussed earlier, pre-copy or post-copy, if they're implemented carefully enough, then the VM can migrate itself. It's not very common, and it's actually very difficult to get this right. But there have been, people have demonstrated that this can be done. So the key thing is, because it's done live, the OS is migrating itself, but then the processes that the OS is running, they're also changing the state of the VM, and the OS itself, just by doing the migration, is changing its own state. So you have to be very careful in limiting the footprint of the migration code so that you don't dirty extraneous memory. And then there has to be something like a two-stage commit, just like for databases, you have two-stage commit. Similarly, you need a two-stage checkpoint and copy operation for self-migration. So I just want to take this a little further to give a bigger picture. So far, we were talking about just one VM being migrated from one machine to another machine, right? But in practice, if you look at a large data center, they have racks of machines, and each machine may be running many virtual machines, right? So if you're going to shut down an entire rack, which is running thousands of VMs, they all need to be migrated to another rack, and they all need to be migrated together, and they all need to be kept live. So when you scale up the problem from one VM to multiple VMs, then the problem becomes very hard. Also, the destination machine may not be ready to receive all the VMs. Like, it may be slower than the source machine, right? The source VM wants to send the source machine wants to send the VMs out very fast, but destination is slow. It's not ready to receive all the VMs. So scatter gather migration is one approach where this is still a single VM approach, but the idea here is that the destination is slow. The source wants to get rid of the VM as quickly as possible. Maybe it's going to fail. So you want to send the VM out before a hardware failure. What it can do is it can scatter the VM out to some intermediate nodes. So there may be many machines in the network. You can take VM, break it up into pieces, and send it to many other nodes in the network. And at the destination, you can kind of gather the VM from all these intermediate nodes. It's called scatter and gather. But the source scatters the VM, and the destination gathers the VM. This way, the source can push the VM out as fast as possible. In the destination, because it's slower, it can gather the VM at its own pace at a later time. So this is another interesting design point to consider. And you can, of course, scale this to many VMs. You can scatter many VMs and gather many VMs at different locations. So, and there's another case when I mentioned like multiple VMs being migrated. You have a group of VMs here that are at the source machine that need to be sent to a target machine. So if we do it all at once for each VM, there will be so much data transferred over the network that it can pretty much bring down the network. This is a very common problem. You don't want to bring down a production network just because VMs are being migrated. So you have to do everything possible to reduce the amount of traffic going over the network. One observation is that all these VMs may be running similar operating systems, like all of them may be running Linux, for example, right? Which means a lot of their code and data is identical. So if we can identify ahead of time, if we can identify all the pages that are identical across all the VMs, then we can just, instead of sending the same page n times, like with a regular migration, we can send it one time. And then at the destination, we can duplicate it. So that way we're reducing the load on the network by sending less data, right? And of course, the challenge is, how do you identify pages that are identical? This is called deduplication. which means that somebody has to be comparing the contents of different VMs, the memory pages, whether they're identical or not, and then keeping track of that. That is an expensive operation. So you have one page here and one page there, and likewise. So you want to compare across all the VMs and figure out, oh, they're all the same, so I'm going to keep a copy. So that's a computation intensive operation. You either have to do a raw copy mem compare, or you may have to compute some kind of a hash function, a checksum on the contents of a page, and then compare the checksum values instead of comparing the entire page. If the checksum matches, then you can proceed to compare the contents of the page. So doing deduplication can save a lot of network bandwidth, and it can also speed up the migration because you're sending less data over the network, so the entire migration can be finished faster than if you were to transfer each VM individually.